Welcome to Math for Engineering Technology. What is this course? This course, well, first of all, as the name might suggest, is for tech majors, particularly civil tech, energy tech, biomed equipment tech, any kind of tech majors. And it's a combination, really, of algebra. Used to be you guys all had to take college algebra, and that was considered kind of dumb, because there's other things you need besides college algebra, and most especially, you don't really need everything that's in college algebra. So what we did is we took algebra, we took trig, because you definitely need some trig, some use of trig, and we actually took a little bit from statistics. So this is kind of a combination of three classes. You get some algebra work, you get some trig for sure, and we're going to get a little bit of statistics, just a little bit. Our first unit, in fact, is going to be statistics. As you can see here, concepts of probability leads into statistics. So, why statistics? Well, in a tech context, there's at least two big applications of probability statistics stuff, and the first is called QC, or quality control. You've got an assembly line or something, you're making some stuff and you want to make sure they work. Now, if you're making chips for satellites, you're probably going to test every single one. But if you're making chips for some consumer product and you're selling millions of them, you're not going to test every single one. So what you'll do is you'll sample off the assembly line or something, and then you have to make a decision. Hey, we seem to have a certain percentage of defective widgets here. And then you have to decide, is that acceptable? Is 0.01% defect rate acceptable? Probably. Is a 2% defect rate acceptable? Well, it might be. I don't know. I mean, it depends what you're doing, of course. Like, you know, you got to make sure that only X% of people find a bug in their peanut butter, but, you know, whatever. There's, you know, a certain number of your radios have to work, you know, whatever. So anyway, QC is a big one. Another big area, which might sound related, but it's actually a little different, is testing. Testing in the sense of, hey, I'm building a bridge. How strong are the gusset plates? You want to know that, right? How much weight on the bridge is it going to take to break the gusset plates? That's important to know. And the thing about testing is, you're not just going to take one gusset plate and see how much it takes to break it, because if you only measure one gusset plate, well, theoretically, it's infinite uncertainty, because you have no idea whether you just happen to grab a random plate that was really, really strong or even really, really weak or whatever. You have no idea. So what you have to do is you have to measure it, you know, at least 4 or 5 or something, break them, randomly selected preferably, and then you break them all, and then you get some kind of average, and then you put some kind of error bar on your average. So it's like, oh yeah, this gusset plate will hold 1,000,000 pounds, plus or minus, what is it, 5%, 10%, 20%? You know, you need to know these things, so that way you can predict the chance that the bridge is going to hold, which you want to be a really, really good chance, by the way. But anyway, testing is a big one. QC is a big one. So this will be our shortest unit, actually. I'm only going to do like a half dozen lessons or so, just enough to give you sort of a grounding in these probability concepts, so that if you ever do go into testing or whatever, you'll be able to talk the talk a little bit as you get started or whatever, just to have a fundamental understanding of this stuff, just to have a feel for it. So we have to start with probability, and it turns out to calculate a probability, it's all about counting. Counting is the thing. At its most basic, calculating a probability, saying what's the percent chance this is going to happen, is, well, you have to do some counting. So for example, let's start with some basic dice. Biff rolls a standard 6-sided die. You know, the kind you get in most game boxes. What is the probability that he rolls a 1? Okay, so 2 questions that you always ask. Question 1. How many ways can we get a 1? And I'll actually draw it. How many ways can you get a 1? And, well, just one. But the other question you have to ask is, how many outcomes are possible, because you might not get a 1, you might get something else too. So you have to count how many outcomes are possible. All the outcomes that are possible, whether they're a 1 or something else. And so you can think in terms of, well, it's a 6-sided dice. I'm either going to roll a 1 or a 2 or a 3, or I might roll a 4. I could roll a 5, or maybe I'll even roll a 6. And so there's 6 possible outcomes. And so you put this together like this. You say the probability of getting a 1 is, there's one way to get a 1, there's 6 things that could happen. It's 1/6. It's a 1 in 6 chance, you might say. It's a probability of 1/6. Now, often probabilities we're going to convert to decimals. How do you convert a fraction to a decimal? 1/6, you go 1 divided by 6. Your calculator will say 0.167. Usually 3 decimal places is going to be pretty good. And then as a percent, you would just slide it over twice, right? 16.7%. So you could say 1/6, you could say 0.167, you could say 16.7%. We will be going back and forth between all 3 ways of expressing probabilities as we go through this unit. But that's the basic idea. You're counting. You're counting 2 things. How many ways can I get what I'm looking for, and how many things might happen total. Let's look at a couple more examples here. Barney rolls a pair of dice, 2 of them. And so what's the probability he gets a sum of 7? Okay, well, I always think about what I'm looking for first. So question 1, how many ways to get a 7? How many ways to get a sum of 7, if I want to be precise? So you have to think in terms of, well, how would the dice add up to 7? It could be that I got a 1 and then a 6. Or maybe I got a 2 and then a 5. Or maybe I got a 3 and then a 4. Or maybe I first got a 4 and then I got a 3. That's different, right? Each dice is doing something different here. Or maybe I got a 5 first and then a 2. Or maybe I got a 6 first and then a 1. So if you count those all up, there's 1, 2, 3, 4, 5, 6. There's 6 ways to do it. 6 ways. Question 2. How many rolls are possible? Now there's a lot of rolls that are possible. I'm not going to actually list them all, but I'm going to start to list them all so you can see how I'm coming up with this number. So you have to think in terms of, well, I could get a 1 and then a 1, or maybe the first die is a 1 and then I get a 2, or maybe I get a 1 and then a 3, or a 1 and then a 4, or a 1 and then a 5, or a 1 and then a 6. Or maybe the first one comes up at 2 and then I get a 1, or a 2 and then a 2, or a 2 and then a 3, or a 2 and then a 4, or a 2 and then a 5, or a 2 and then a 6, all the way down to you might get a 6 first, a 6 and then a 1, a 6 and then a 2, a 6 and then a 3, a 6 and then a 4, 6 and then a 5, 6 and then a 6. Okay. So if you imagine that I listed everything, including starting with the 3, starting with the 4, starting with the 5, there's actually 36 different things that could happen. And so maybe I'll switch colors here for a bit of emphasis. The probability then of getting a 7 would be there were 6 ways to do it, and there were 36 things that could happen. And so the probability is a 6 in 36. Now, one of the things I will insist upon is that you reduce your fractions. It's a 1/6, right? You can cancel the 6 top and bottom. By the way, while we're at it, here's my favorite calculator. Casio FX300 ES. The ES is the most important part. Casio is probably the second most important. Well, Casio and ES are equally important. The FX300, you could also use I think it's a 115, but 300 is a good one. It's like a $15 calculator maybe. And if you on your calculator were to have written 6 divided by 36 like this, it would actually give you the fraction 1/6. It would reduce it for you. That's kind of the point I'm trying to make. By the way, if you wanted the decimal, you would hit the SD button, and then it would do the 1 divided by 6 for you, and it would show you the 0.166666666, which we can round to 0.167. 1 divided by 6, of course, is the same as it was up there, and 16.7%. There. So there, I just put my pitch in for the calculator. It's a good one, trust me. I did ask the store to stock them, but they always charge like a 25% profit margin, so you probably don't want to go there. You probably want to go to, I don't even know who has it these days. Used to be office stores had them. Target used to have them. I don't know. Walmart. They keep changing their stock, you know, but that's the one you want. Get it from Amazon if you have to. It's a good calculator, trust me. Okay, now actually, before we leave this example, this is worth pointing out. P.S. I'm going to ask you, what is wrong with this picture? Let's say we were starting fresh on this problem. We said, oh, Barney rolls a pair of standard six-sided dice. That's cool. He's going to roll a 7. What's the chance he rolls a 7? Let's figure it out. Hey, I'm trying to erase you. I'm trying to erase you. Okay, let's figure it out. And let's say you took this kind of approach. You say, well, I know that when I play Monopoly or whatever, the lowest you can get is a 2, right? You have to roll a snake eyes, a 1 and a 1, in order to get a 2. But you could also roll a 3 or a 4 or a 5 or a 6 or a 7 or an 8 or a 9 or a 10 or an 11. You could also add up to 12 if you got box cards, 2 6s, right? You would add up to 12. And so if you say, okay, that's all the possible results, and getting a 7 is only one of them, and so the probability of 7 would be there's one way to do it out of, what is this, 11? 1, 2, 3, 4, 5, yeah, 11. It's a 1 in 11. What? Why are we getting such a different answer? It's supposed to be a 1 in 6, right? It's supposed to be over here. It's supposed to be a 1 in 6. Why are we getting a 1 in 11? Well, there's a problem with doing it this way, and you want to be aware of this problem so that you don't mistakenly do something like this in a different situation. The problem with this is that, think of rolling a 2. You have to get a snake eyes. You have to roll a 1 and a 1. That's the only way to get a 2. Or think of rolling a 12. You have to get boxcars. You have to get a 6 and a 6. Now think of all the different ways you might roll, say, a 5, a 1 and a 4, a 2 and a 3, a 3 and a 2. See, there's different number of ways to get these things. I don't want to say that. Yeah, there's lots of ways to get a 4, to get a 6, to get a 7. So they're not equally likely. So this does not work. And I think I'm going to try to go back to a pen here. I'm going to cross that off. Outcomes must be, and the official phrase is equally likely. And that's why this way worked fine, because getting a 1 and a 1 or getting a 2 and a 2 is exactly the same chances of getting it, because the first one is a 1 and then the second one is a 1. There's only one way in 36 to do that. The first one is a 2 and the second one is a 2. There's only a 1 in 36 of doing that. The first one is a 2 and the second one is a 4. There's only a 1 in 36 way of doing that. But here, getting a 5 for a sum, there's different ways to do it. There's a number of different ways to do it. And there's a different number of ways to get a 4, and there's a fewer number of ways to get a 3, and there's only one way to get it. It's not all equally likely. Outcomes must be equally likely. It won't work if it's not. So this is an important point. You know what? You know how I'm asking you to turn in your notes? Make sure that point is in your notes. Okay? Make sure it's in your notes. Outcomes must be equally likely. When you go counting these things, make sure you're counting equally likely outcomes. Okay, let's go to a different example here. What do we got? We've got an urn, and it's got marbles in it. We got some blue ones, we got some green ones, got some purple ones, we got some orange ones. Okay, cool. And we're just gonna grab a marble at random, just one marble. That's fine. So question A, what's the probability that he gets a green one? Well, question 1. How many ways can he grab a green one? And you look and you say, well, there's 50 green marbles, so picking any one of those 50 would count as grabbing a green one, right? So there's 50. 50 ways to grab a green one. Question 2, how many could be grabbed? How many total? How many total marbles can be grabbed? And now you have to start saying, well, I could have got any one of those 40 blue ones, or any one of these 50 green ones, or any one of these 60 purple ones, or any one of these 70 orange ones, that adds up to what? 40, 90, 150, 220. That adds up to 220. So there's 50 ways to get a green out of 220 things that you might do, and so your probability of green is 50 out of 220, which you do want to reduce. Please always reduce. So cancel 10s, basically cancel the zeros off. So 5 and 22. If you go 5 divided by 22, you'll get equals about 0.227 if I round to 3 decimal places. And that would be, whoa, what'd you just do? And that would be 22.7%. Okay, 3 ways to express your answer. I think in the homework I'm going to ask you to express it all 3 ways. What is the probability that you do not get a purple one? Not. Okay, so how many ways can he grab a, well, if it's not purple, then I'm going to say it's non-purple. How many ways can he grab a non-purple? Well, let's come back up here and start adding again. That's not purple. That's not purple. Those are, but those aren't purple. So you add 40 plus 50 plus 70, you get 160. So there's 160 ways to grab a non-purple. And of course, it's out of the same number of marbles, 220. And so we've got 160 out of 220. Reduce. 16 out of 22. Reduce again, right? You can cancel 2s. 8 out of 11. Okay, so your probability is 8 out of 11, which if you make it into a decimal, 8 divided by 11 comes out to 0.727, or just about 72.7%. For now, I think it's going to be it's going to work well to just use 3 decimal places, and then your percentage will come out to have 1 decimal place, right? After you move it twice. Whoops. What do I redo? Hey, that was cool. Okay. Here's another one. The old deck of cards problem. So just in case some of you don't know what a deck of cards looks like, there's usually 1 or 2 people who don't. There's what a deck of cards looks like. This is a standard deck of playing cards. Notice we got 4 suits. Whoops. Cut that out. Okay, this is called the suit of spades. This is called the suit of hearts. This is called the suit of diamonds. This is called the suit of clubs. So spades, hearts, diamonds, clubs. This is called the ace, which is another name for 1 ace. Of course, you see a 2, 3, 4, 5, 6, 7, 8, 9, 10. This is called the jack. This is called a queen. This is called a king. J-Q-K. Jack, queen, king. So there's what a standard deck of playing cards look like before you shuffle it all up. Now, that's going to be sort of our pool that we're drawing from here. So Bess has a standard deck of 52 cards. That's that. And she randomly grabs a card. So blindly, maybe shuffles the deck or whatever, and blindly grabs a card. Let's see what we got here. Probability of getting hearts. Well, question 1. Oh, let me turn the page here. Turn the page. How many hearts? How many heart cards, I might ask. How many heart cards could is this a she? Yep, Bess. Could she draw? Well, you can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13. Question 2. How many total cards? And it says right there it's a deck of 52. Notice it's 13 in each suit, and there's 4 suits. So 4 times 13 is indeed 52. So if you were to take the probability of getting hearts, it would be 13 out of 52, which you would reduce. Notice you can kind of see just by looking at the diagram that it must be a 1 and 4, right? Because just think in terms of rows. There's 1 row of hearts. There's 4 total rows. So it's a 1/4. 1/4, of course, is 0.250 or 25.0%. There. What is the probability again? A face card. So part of what we're doing here is we're introducing terminology. All of these things, the jacks, the queens, the kings, notice they got faces on them. And so we call them the face cards. So how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12 face cards. So there's 12 face cards in a deck of 52. You would reduce that, cancel 2s. 6 out of 26, you would reduce that, cancel 2s. 3 out of 13. Okay. 3 out of 13 is the probability of getting a face. And as a decimal, 3 divided by 13 is about 231. So that's like a 23.1%. So it's almost a fourth. Wow. Probably a face card, 0.231. And one more. Best removes. Oh, this is different. I'm going to get a different color pencil out here. She removes the red face cards from her deck and then selects another card. Okay, so before I even read on, I'm going to come up here and I'm going to say, she removes, what you remove? The red face cards. So you have to picture, not there, not there, not there, not there, not there, not there. How about if I go like this? There. Now you can tell they're not there, right? She removed those cards, the red face cards. That means the face cards in hearts and the face cards in diamonds. That's what she did. So she changed the deck. Okay. Now, what is the probability of getting hearts? Okay, well, we need the number of hearts that remain in the deck. Remaining. And we're going to need to make the total number of cards remaining. I usually like to have the word total out here somewhere. You always want to think in terms of total on the bottom. And then the specific thing you're trying to do goes on the top, the hearts. We're trying to get hearts. So the number of hearts is, now you have to look at the changed deck. So how many hearts remain? It only goes from ace to 10. There's only 10 hearts that remain. Okay. And how many cards remain? It's not a deck of 52 anymore because we took out 1, 2, 3, 4, 5, 6. So there's 13 here and there's 13 here. That makes 26 plus 10 plus 10, 36, 46. There's only 46 left in the deck. I suppose I should have said 52 take away 6. Anyway, it's a 10 and 46 now. Now that will reduce, cancel 2s to 5 out of 23. 5 divided by 23 is about 0.217. So we're talking 21.7%. Cool. Now, we'll see more of this kind of problem later. This one is sometimes called a conditional probability. And what's conditional about it is that we monkeyed with the deck first. So it's like we weren't just drawing from a deck. First we did something. Hey, let's remove all the red face cards. Then we figure out, okay, with what's left. Then we figured out the probability. Then we did the counting. How many hearts are left? How many cards are left? And so on. So anyway, we'll see more of that later. So, but I mean, for now, you can see what to do. You just say, well, okay, I'll apply your condition then. I'll change the deck. And then I'll count. Fine. No problem. Okay, we're on page 3, I believe. 3 trick questions. These are some common mistakes. You don't want to make these mistakes. Bertha flips a fair coin. In other words, the coin is not rigged or anything. She flips a fair coin 5 times in a row, and she gets heads all 5 times. Wow! She got a heads, and then a heads, and then a heads, and then a heads, and then a heads again. So, question, what does she get next? If she flips again, what is the probability she gets another heads? Well, if you're a gambler, you might be thinking in terms of, well, we're on a hot streak, right? Look at all those heads. This person's getting heads, man. Hot streak. So probably you should bet on heads. That would be one way to look at it. The other way you could look at it is you say, wow, that's lucky. The luck must change. We have to go back to normal, so to speak. You can't get another heads. That'd be crazy. That'd be impossible. Like, so that would mean bet on not heads, tails really. Bet on not getting heads. Okay, so which do you think is right? Is this a hot streak and should bet on heads? Or is the luck bound to change? It has to change. There's no way you could get 6 in a row. That'd be crazy. So it's going to have to be a tails now. Well, the answer is that the probability of heads is always a 50-50 or a 1/2, right? It's either heads or tails. So 1 and 2. Every single time. Assuming it's a fair coin, which we did. So it's always a half every single time. Now, I admit, getting 5 in a row, it's not going to happen very often, but it's kind of like a given. It's like, well, we happen to be in one of those very special situations where Bertha has flipped 5 in a row. It's like, what are you going to do? It's happened. Wow, that's crazy. Do it again. Well, it's probably not going to happen if you try it again right now, right? So just because she's got 5 in a row, that doesn't tell you anything about the next flip. In fact, the flips, another piece of terminology here, are all called independent events. One flip has nothing to do with what happens on the next flip. Hey, I got a heads. That has nothing to do with whether you're about to get another heads or about to get another tails. The chances 1 and 2 every single time. Constant. Okay, so that's one common misconception, I guess, or trap, or whatever you want to call it. Here's another one. Bjorn's looking at the cars in his small city. The cars in his city they're either black, brown, or silver. Nobody has a purple car. Nobody has a yellow car. It's either black, brown, or silver. Every single car, truck, whatever, in the city is either black, brown, or silver. So, what is the probability that the next car to drive by, which is kind of like saying pick a car, any car, right? Because we assume it's a random car that's going to drive by. What's the chance that this next car to drive by is going to be silver? Well, I suppose you might say there's 3 colors, right? So silver's only one of them. So it'd be a 1 in 3. No, it wouldn't. We don't know that. I suppose theoretically it's possible, but we don't know that. Do you know why we don't know that? Think back to the what now? Think back to when we were rolling 2 dice and saying, what's the chance of getting a 7? Remember we said you list all the possibilities, but you got to make sure you list all the possibilities so that they're equally likely. The problem is we don't know how many black are there, how many brown are there. Oops, that's supposed to be a question mark. Oink, oink, oink. We don't know how many silver there are. Like if we have 1 black car, 1 brown car, and 5,000 silver cars, wouldn't be such a small city, but if we had 5,000, the chance that you get the next one's going to be silver is pretty darn good, right? It would be actually 5,000 out of 5,002, which is almost certain, not certain, but almost certain that it'll be a silver one. So in other words, we need to know these numbers before we can calculate the probability that it's silver. We have to know, well, how many are black, how many are brown, how many are silver. So don't just take the 3 categories, black, brown, and silver, and say, well, it's got to come from one of 3 categories, so it's got to be 1 out of 3. It's like, no, it's not 1 out of 3. It's, what are you going to call this? Insufficient info, something like that. What did I say over here? What did I say over here? I said indeterminate. You could say indeterminate, or you could say insufficient info. That somehow sounds better to me this time around. Insufficient info. Okay, this next one. This is a great one for winning money at the, at the Buffalo Wild Wings or whatever. Family has 2 kids. Okay. We know that one of them's a boy. So what's the chance the other's a girl? What's the probability the other one's a girl? Now, 2 hints. Hint. It's not a half, which took me a long time to believe this, but because you think in terms of, well, a boy or a girl, it's a 50-50, it's a 1 in 2 chance of getting one or the other, and we're just saying, what is this, a boy or a girl? Well, it's got to be a 50-50, it's got to be a 1 in 2, and it's like, no. So the other hint is, how should I say this? It's all in the phrasing. You got to really bear down and look at the phrasing here. It's like, what are they actually saying? Are they actually saying, hey, what's the chance that a kid is a boy or a girl? That's not the question. That's not actually the question. We have this condition here. We know that one of them is a boy. Well, we have 2 conditions, really. There's 2 kids, and we know that one of them is a boy. So, if we have 2 kids, and we know that one of them is a boy. Okay, well, first of all, if we have 2 kids, how many ways can you have 2 kids? Well, you could have the first one be a boy and then the second one be a boy. This is like rolling dice again, right? The first one could be a boy and then the second one a girl. Or maybe the first one's a girl and then the second one's a boy. Or maybe the first one's a girl and the second one's a girl, right? That's the way you can have 2 kids. You got 4 different ways of having 2 kids. We know one of them is a boy. Means this is not possible. This is not one of our possibilities. So notice that we've only got 3 possible outcomes here. This family is either boy, 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 girl, or girl, boy. It has to be one of those 3 because we said it has 2 kids and one of them's a boy. So those 2 conditions change everything. They change the counting. So you have to be very careful about how you do the counting. So now the question, what's the probability the other is a girl? So this one's a boy, pardon me, and the other one's a girl. This one has a boy and the other one's a girl. This one doesn't. This one, they're both boys, so you don't have a girl at all. So notice that the probability is actually a 2 in 3. How about that? It's a 2 in 3. Whoa! As a decimal, 0.667. As a percent, 66.7%. Oh, I love that one. I love that one. Okay. Usually I love the problems that took me a long time to figure out myself. Then I see it and I go, oh! And then I kind of fall in love with it. Anyway, okay, we're kind of done talking about probability and how you calculate probability, but we need to bring up this one other word called odds, because odds, you see odds, well, usually like at a racetrack or a casino or something, card games, whatever. You see odds come up, and they're not really the same thing as probability, so let's just get that distinction across. So if they say, for example, let me do a completely different color. Here we go. The odds of winning the big prize are 1 in 4 in favor. Well, 1 in 4, notice we use that colon when we're talking odds. 1 in 4 in favor, what does that mean? What it means is 1 way to win and 4 ways to lose. That's what it means. So they're making a ratio of sorts. They don't use a fraction, they use a straight line ratio. But the thing is, remember, for probabilities, you do the number of ways of winning over the total number of outcomes, which is not the same as the number of ways of losing, of course. So the number of ways to win is 1, and then the total number of outcomes. You have to go like this. Well, there's 1 way to win and 4 ways to lose. That's 5 things that could happen. Okay? 5 possibilities. Let's maybe emphasize that. 5 possible outcomes. Exclamation point. 1 way to win, 4 ways to lose, that's 5 possible outcomes. You use the number of possible outcomes when you do probability. So the number of wins over the total number of outcomes is 1 in 5 actually, 0.200 or 20.0%. So dig on it, man. It's a 1 in 4 comes out to a 1/5. A 1 in 4 in favor means a 1 in 5 probability. Okay, maybe you've got the idea now. Let's look at this one. Maybe you want to try that yourself. I don't know. Pause. Come back. So the odds of a fish fry being any good are 5 to 1. Well, there's a twist. Against. The odds are against. That means it's more likely you won't, right? So it's 5 ways to lose. Actually, to not find a good fish fry. 1 to win, to yes, find a fish fry. So that word against is kind of switching the lose and win around. So up here, again, in favor means, well, in favor, 1 way in favor, 4 ways against. 5 to 1 against, 5 ways against, 1 way to win. Okay. So let's see now here. 5 to lose, 1 to win. So that would, of course, be 6 total possibilities. Just add them up. And what is the probability of finding a good one? Well, you want to put the number of ways that you do find a good one, which I call winning, over the total possibilities. It's a 1 in 6th. We've seen this decimal before, 0.167, 16.7%. One last one. So here we're given the probability. We want to get the odds. Okay, so it's just same thing, only backwards. Brynja plays Bridget in a friendly game of chess. According to their ELO ratings, Brynja should have a 60% chance of winning the game. So probability that Brynja wins, how the heck do you spell Brynja, is 60%, which as a ratio is 60 out of 100, right? That's what a percent means, which we can reduce to 6 out of 10, which we can reduce to 3 out of 5. Okay, so that's 3 wins, 5 total games. That's what probability means. It's the number of wins over the total number of outcomes. Okay, so that's just interpreting what they said. They said 60% chance of winning. That means a 3/5 chance of winning. That means 3 wins out of 5 total games. That's what that all means. Cool. What do they want? What they want is odds in favor of Brynja winning. Okay, odds in favor. They didn't trick us by talking about Bridget instead. I like that. We're talking about Brynja still. So odds in favor for Brynja, I'll say. I assume that's Brynja, not Brynja, but whatever. Odds in favor for Brynja are 3 ways to win. How many ways to lose? Right? Remember, it's a lose to win or a win to lose situation. Since we're looking for odds in favor, we put the winning first. Odds in favor, 3 ways to win. How many ways to lose? Well, she wins 3 out of 5, means that she lost 2 games. And so the odds in favor for Brynja are 3-2. Alrighty, I hope you enjoyed our nice little introduction to probability with odds. Go get your homework, please. It's posted in D2L. And actually, we have another lesson for this week. We'll take probability a little bit further. And now I have to figure out how to turn this thing off.